Welcome to our Quantum BW colloquium. My name is Niklas Schillo. I'm part of the team Quantum Computing at Fraunhofer IAO, and I will guide you through today's colloquium. So Quantum BW is a state initiative in Baden-Württemberg for quantum activities that has the goal of bringing these technologies together and creating an umbrella brand to strengthen those networks and also to increase the visibility of Baden-Württemberg as a quantum technology hotspot in Germany. And with this colloquium here, we want to promote the scientific exchange between algorithmic topics and also hardware topics in the field of quantum computing. And we also want to present the latest developments in this scientific field. And today I have the honor of introducing Professor Dr. Ioan Pop from KIT and University of Stuttgart. In 2011, he completed his PhD at NEIL Institute of CNRS and the University of Grenoble in France. And in the same year, he became a postdoctoral associate at Yale University. From 2015 to 2020, he led a startup group supported by the Alexander von Humboldt Foundation. And now since 2020, he is a research group leader at the Helmholtz Association. And we are very happy to have you here today, Professor Pop. He will now introduce us to superconducting quantum hardware with his talk called Mesoscopic Physics Challenges in Superconducting Quantum Devices. And in this talk he will give us an introduction to superconducting quantum devices, and he will explain three effects which complicate the task of engineering coherent superconducting devices. Those are ionizing radiation interaction with the qubits device substrate. Also he will talk about two-level systems which imprint a memory in the environment of the qubit, and also he will talk about fluctuations in the transparency of the tunnel barriers in the Josephson junction. If you have questions during the talk, especially if you're online, please ask them in the online chat. I will read them in the end of the presentation. And with this, I will hand over to you, Professor Pop.
Thank you. Thank you for the introduction. It's a pleasure to be here. Hello, everyone online. Please don't be shy. Please ask questions during the talk. It will actually make my life easier to see if you guys are following, to see what is more interesting for you, or to see if something is not clear. So, as was mentioned in the introduction, I'm a joint professor between KIT and Stuttgart University. So at KIT we have a lab in the Helmholtz Association, and in Stuttgart my office is a few buildings from here. So if you want to have follow-up discussions, don't hesitate. We can easily meet. The title of my talk, as you can see, can be read in two registers. So it can be read in a more neutral register, Mesoscopic Physics Challenges in Superconducting Quantum Devices, or the way I take it personally, in a more personal challenge register, Mesoscopic Physics Challenges Superconducting Quantum Devices. So challenge accepted. Okay, so that's what I'm going to talk about today. And I think one of the things that one can understand from popular culture nowadays, and from looking at press releases from companies, and also not only from companies, also from academic groups, you might think that quantum technology is all about engineering now, right? You might think that the basics are understood, and now, okay, now we just have to find some really talented and hardworking team of engineers, lock them in a building, and then it will be something like the Manhattan Project, and in 2 years or 3 years we have a quantum computer. I'm here to tell you that it's probably not the case. I'm here to tell you that there are so many things at the most basic level that we are still not understanding, that the road ahead will be challenging. Right? So I think engineering and scaling up is very important because it allows us to discover new challenges and to play more interesting games with these qubits. So the kind of games we play with 1 qubit or with 5 or 10 qubits are quite different. And it's really cool to have the support of companies who are building these demonstrator devices with tens of coupled qubits to play with. But we should not forget that the fact that we are trying to build demonstrators with tens of qubits, we should not forget that that does not mean that we solved the single qubit. The single qubit is very much an open challenge. And that's what my talk will be about. So in my talk, you will only see single qubit experiments, and you will see what kind of problems we encounter. So what makes a bit more difficult this quest is the fact that, as Steve Gervin, one of my mentors from Yale, is saying, quantum weirdness is not a bug, it's a feature. Like that's what we are looking for, right? So but it's a feature, but it makes our life difficult because our brains don't have the intuition for quantum, right? Our brains have a classical intuition. So it happens many times that in our daily life, we as scientists, we imagine an experiment, we do the measurements, we see some result which we find a bit surprising, and we're like, I was not expecting that. But then we think about it a bit more rigorously, we write down the equations, and then we see that, okay, that's what actually quantum mechanics predicts. This weird thing that we measure is actually correct. But it was very difficult for us to find it, to have let's say, a natural expectation or to have an intuitive expectation for that result. Right? So that's, I would say, the biggest challenge in teaching quantum technology and in building a community is to actually gain this intuition about quantum mechanical effects beyond all the very tough engineering challenges. So in some sense, our quest for the qubit is, of course, history never repeats itself, but some patterns in history repeat. So I think there is a pattern that is repeating now in superconducting qubit technology and quantum computing technology in general, which is the pattern that we also saw when people were inventing flying machines. So we are here in Stuttgart, like 3 hours and something by train from Paris, and I really recommend, if you have a weekend available and some money for the fast train, I recommend to visit the Musée des Arts et Métiers in Paris, which is close to Gare de l'Est, where the train arrives from Stuttgart, and to look at this machine. It's in the hallway of the museum. It's a very impressive machine to look at, and it's one of the first. It's before the Wright brothers, right? So this is several years before the flying machine of the Wright brothers, and it looks really cool. It's a very fine engineered machine with the highest tech of the 1900s integrated inside it. And it's a very smart design because you see the wing doesn't have some random shape. The wing has a very well calculated shape resembling basically the wing. If you look at eagles, how they soar in the sky, that's basically the shape of their wings, right? So this was not some funny naive experiment that you sometimes see in old movies where someone puts some wings and jumps off a bridge, right, and flaps their wings and they don't fly. This was a very well-designed experiment, but it didn't work. It didn't work, and the army, the French army funding the project actually cut the funding. They were not impressed, even though this thing kind of flew like a few meters off the ground, but then it landed and rolled over and completely destroyed itself. The Army Research Office, the French Army, was like, this is never going to work. And even if it works, what are we going to do with it? It's not really useful for anything, right? So, and 40 years later, wars were fought in the skies, right? So this just shows you how quickly things can change and how narrow, in some sense, the vision of humans can be when they're inventing a new technology. And why didn't it work? Well, because of this wonderful, basically this is like jewelry, this engine that you see here, it's all made out of aluminum. It's a really state-of-the-art. It's maybe even now it's probably the highest performance steam engine in terms of power versus weight. But it was a steam engine. That's why it didn't work. Because steam engines are very, very heavy, right? They have to carry water to make steam. And what worked was this contraption, which looks much less professional from the Wright brothers. It looks like something that you put together with shoelaces and chewing gum. Even the tail of the apparatus is in the wrong direction. You see the human is facing this way, and the tail is in front, which of course makes it highly unstable. So they very quickly realized, okay, we have to flip that around. But this thing worked. Why did it work? Because it had an internal combustion engine. It had a completely different type of engine. It had the kind of engine that you have now on a lawnmower, for instance. So that was the kind of really technological breakthrough or complete change in vision that allowed humans to reliably take to the skies. So what is the workhorse for us, right? What is the workhorse for superconducting hardware and superconducting quantum circuits? It's the Josephson junction. So for those of you who know, I apologize, this will be very basic. For those of you who don't know, here's what a Josephson junction is. It consists of some thin film of superconducting electrode 1, the one in red, let's say, then a second thin film superconducting electrode number 2, and these two electrodes are separated by a very thin insulating layer. Typically, in our case, it's made of aluminum oxide because the electrodes are made also of aluminum. So everything is sitting on a substrate, which can be sapphire or silicon or something else. And we use, to fabricate these objects, we use microelectronic techniques. So we use exactly the same techniques that people use to fabricate transistors. Okay, so in reality, once we fabricate a junction like this and we take a scanning electron microscope, this is how it looks like. So you see the bottom electrode here. This is false colored, of course. So the red part is the bottom electrode, and it's covered by the blue colored electrode at the top. And the overlap right here, so this is a view from the top, right? So the overlap gives the junction area. So in between the blue and the red, you have the oxide. Okay, that's our workhorse. Why do we need that? Well, because we need nonlinearity. We need, just like in the transistor, you have nonlinearity to be able to do computation. We need some kind of source of nonlinearity for quantum devices. And the easiest way to think about it is that this junction, which here we denote by this symbol X, if you're a physicist, you know exactly what's happening. If you're an engineer, you don't have to worry about it. This X you can simply replace with an inductor. So it's really just a coil, right? You can put here a coil to think about an equivalent circuit. And then this object that you have here, you immediately recognize it's an LC oscillator, it's a harmonic oscillator. And now what the difference between a junction and just an inductor or a coil is the nonlinearity. So the reason why we use Josephson junctions is to add a little bit of nonlinearity to this this inductor, such as that when we put a photon in this harmonic oscillator, when we put the first photon in this harmonic oscillator, it has one frequency and some current flowing through the junction, right? When we put the second photon, the current through the junction increases, through the inductor increases, because we have more energy, right? If the current increases, the nonlinearity of the junction makes the inductance higher, and that actually shifts the frequency lower. So the frequency for the first photon has one value, and the frequency for the second photon, because it has there's more energy circulating in the device, actually has a different value. Quite significantly different, by a few percent. And a few percent sounds like a little, and it's not that much, but in our world is actually a lot, because what we compare it with is the line width, right? And the line width of this harmonic oscillator, which is slightly anharmonic, the line width is part per million, right? So we have quality factors of hundreds of thousands or a million. So when you have a percent shift of something that is defined with part per million, you're going to resolve it, right? It's going to be a very distinct peak in your spectrum. And that's how we operate with these objects. We have one frequency for the first photon, one frequency for the second photon, and that's what allows us to reliably put only one photon just by driving at this frequency, and to do quantum operations and to create superposition states of one photon being in the device or not being in the device. Okay, so that's all there is to it. That's the superconducting qubit in a nutshell. Everything else is details and technology. So if you have questions about the functioning, the basic functioning, now is a good time. All clear? People are familiar with the harmonic oscillator? Yeah.
I have one question. So where do the TLS arise in this?
Oh, TLS. Well, this is a TLS. This is a two-level system, right?
Ones, right?
So this two-level system we engineer and we want it there, yes. Right? Now, what you're referring to are all the other possible oscillators and degrees of freedom that could be in this object which has billions of atoms, right? So you see what I have done here, I have taken billions of atoms in this oxide, in these electrodes, in the substrate, and I just said that all of these billions of atoms, each of them with several degrees of freedom, rotational, vibrational, whatever, I said that all of this complexity, many orders of magnitude, I can just ignore it, and what I have is 1 degree of freedom. One oscillator, phase, the phase of an oscillator, 1 degree of freedom, right? So I made a simplification by Avogadro number orders of magnitude. So I have a 10 to the power 23 simplification right here. So of course, there is a huge discrepancy between this very simplified model and the actual reality. Like what happens on a microscopic level for each atom in this system. So each atom has the potential to actually not fall in line and obey these collective dynamics that I'm describing. It can decide to do its own thing and become its own quantum bit, which then is coupled to our quantum bit. And that's a problem because we have methods to control the dynamics of this object by engineering antennas, by engineering voltage biases, things like that. But we don't have the tools implemented to control single atoms in these devices. So they will just do their own thing. So our goal, and that's basically what the talk is about, our goal is to identify these rogue players, these rebellious atoms who don't, rebellious degrees of freedom, and figure out what they are, where they are, how they behave, and maybe figure out ways to suppress them or disconnect them from our qubit. Okay, I don't think I answered to your question, but I delayed the answer for later. Yeah, because you will see the origins of these two-level systems are multiple. I have a slide about that. Any other questions? Good. So since the first implementation of a qubit in basically around the year 2000, it has been an exciting 2 decades. So many things have happened. We have gone from lifetimes, and what we call lifetime is how much the energy stays in the qubit, that's T1, and how much a superposition state resides in the qubit. So if you create a quantum superposition state between 0 and 1, so it goes somewhere in the middle, how long can you track this superposition state in time? So this is T1, T2. So these coherence times T1, T2, they have increased from nanoseconds in the early 2000s all the way up to milliseconds nowadays, right? So that's a huge progress over 2 decades. And I would say they are still increasing. So it's sometimes difficult to really judge that because now there is a little bit of a branching. So academic heroes keep increasing. So if you just look at single qubit implementations where people really care about coherence and they try to push these numbers T1, T2, there is progress. Every few years there is progress. The latest breakthrough, I would say, was the realization that that you can remove some of the surface losses by using other superconductors, not aluminum, but tantalum or niobium or some aggressive cleaning methods. And this was just a few years ago, which allowed a factor of 5 to 10 increase in T1 and T2. Okay? So things keep improving. But the other branch is industrial processors, where people, let's say, in companies, they commit to some technology, then they build a roadmap based on that technology, which lasts for 5 or 10 years, right? And during that roadmap, there won't be spectacular changes in the coherence because they have more or less committed to a particular technology. What will change will be the scaling. They will build bigger and bigger and bigger devices and try to maintain the coherence, level as they increase the scale of the device. Okay, so that's why I think, this is of course an oversimplification, but that's how I see these two directions, and there is still a lot of progress in coherence. So, as I mentioned when I addressed your question, quantum computing devices try to run away from the complexity of mesoscopic physics. So in our case, for superconducting hardware, it's really obvious. But even if you think of much more point-like, let's say, quantum bits like trapped ions, even there, it's not just a degree of freedom. Even for trapped ions, you have the trap itself, which is a solid-state device. And when you start to miniaturize trapped ions, you start to have, even though you're addressing a single ion, you start to have solid-state physics problems, which are introduced by the trap itself, by the electrodes of the trap, by the metal of the trap. Right? So we're always trying to run away from the complexity of mesoscopic physics. And one very successful strategy in the last 15 to 20 years, was to build this object, which is very simple. It's called a transmon qubit. Maybe you've heard of it. It simply consists of a junction. You can see it here. It's the same type of junction that I've shown you before. It just has a different geometry now. So before, the two electrodes were like this, and now they're aligned like that. It doesn't matter. It's just another trick to fabricate it. And I colored the top electrode with yellow, the bottom electrode with blue, and you can see the junction here. It's 200 by 200 nanometers. Okay? And a transmon qubit consists of one of these junctions in the middle of two large pads. That's it, which form a capacitor. So that's your slightly anharmonic oscillator. And this is what I was explaining before with my hands. Now you can see it here a bit more concretely. So you see that the first transition in this anharmonic potential has a higher energy than the second transition. And this is what we call anharmonicity. This is how we quantify the anharmonicity. It's the difference between these two frequencies. And this is what allows us to control the states of the qubit. Okay, so you see the way the community is running away from mesoscopic physics is by trying, in this case, by trying to shunt. You're shunting and you're diluting any charge noise. So the junction itself, because it's relatively small, will be quite sensitive to charge noise. So if an atom moves in this electrode, if it moves by a few angstroms, it will give you some measurable change in the capacitance of the junction, which will shift your frequency maybe. But now if you shunt this whole thing by a humongous capacitor, now you're just increasing the overall capacitor of the device. So now an atom moving here, indeed it will change a little bit this capacitor, but this capacitor, it's only a small component of this larger capacitor, so your whole device is more stable. So you have not, you see, we have not solved the problem, for instance, of dangling bonds and tunneling atoms in the oxide or in the electrodes, but we have shunted it by adding a huge capacitor in parallel. Okay. So if we see now over the last 20 years, if we have seen an increase in T1 and T2 in the coherence times, that doesn't necessarily mean that we solved these issues. It just means we've shoved them under the carpet and we don't really see them immediately. But if we look under the carpet, and that's what I will do, they're still there, and they can still be quite annoying. So here is what you find under the carpet. If you look, I mean, you'll find more than that, but this is just a selection of three things that you will find. you will find that the environment remembers. So you'll find memory effects in the environment, and that's bad news, because error correction algorithms assume that the environment has no memory. They assume that at whatever point you're looking in, for instance, in a quantum jump trace, when the qubit is jumping from 1 to 0 to 1 to 0, all the current quantum error correction algorithms, they are assuming that it doesn't matter when you start looking at this trace, it will always look the same on average, because there is no memory of what happened to the qubit. And I will show you that's actually spectacularly not the case. Secondly, ionizing radiation changes things, right? So this whole object, this whole chip, is traversed like we are also by muons all the time, even now. There is on average a muon every second going through my palm, right? So, so there are a lot of muons from outer space who traverse at everything at surface level. So this is a problem for our DNA also, and it's a driver for evolution actually. But we have error correction mechanisms in our body which repair DNA that is damaged by this ionizing radiation. Qubits currently don't really have these mechanisms. So when a muon goes through the substrate and it leaves a lot of energy, we will see that. We will see that in the, and we will see the effects of that lasting for a long time. Thirdly, if you look at the junction in a textbook, if you look at what is a Josephson junction in a textbook, it is a cosine phi potential. So it's this function here, right? So energy versus phase, this is the phase drop here. If you want, in the inductor equivalence, it's the flux in the inductor. There is an equivalence there. So the energy of this device versus phase should be a cosine, and the fact that it's a cosine and not a parabola, that gives us the nonlinearity. So it's very important that we know what exactly function that is, right? And it's not only a cosine. That's what I will show you. I will show it's a cosine plus some other cosine functions, which means that the spectrum that you think you have needs correcting. There are some corrections to the spectrum. So let's take them one by one. So now here is an exhaustive list answer to your question. So what can be hiding in the environment of our qubits? So here I'm just showing a photograph, a bit artistic photograph of SEM actually, of one of our qubits. You see we have an antenna here. This is just a line. This is just a strip line antenna which we use to read out the qubit with microwaves in the gigahertz range. That's all there is to it. And then coupled, inductively coupled, you see there is an inductive coupling in the middle. We couple it inductively to this loop here, which has a junction in the middle, and that's our qubit. That's it. So you see, we use a different type of qubit. We don't use a transmon, which is just two pads and a junction. We use what is called a flux qubit, but it still looks very similar. It has a junction in the middle, and now we try to shunt our mesoscopic physics with an inductor, not with a capacitor, but it's a similar approach. And now what we can have there is a lot of physics. We can have magnetic moments. We can have spin-orbit interaction between these magnetic moments, either at the surface of the superconductor or even just on the substrate or in the substrate. We can have radiation, microwave radiation. That's the one thing that we can control. We put the device in a finite element simulator, HFSS, for instance, and then it just tells us what is the microwave coupling to the outside world. So this is, out of all these things, this is the one that we can really calculate and engineer. We can have magnetic moments that are interacting with the condensate. So if you know about superconductivity a little bit, you know that we have these Cooper pairs, which are electrons with opposing spins, which are correlated. But now if you have some magnetic moment which can scatter and interact with one of these two spins in the Cooper pair will not be happy. So that's that will give you some low-lying states, which will act again as some two-level systems. We can have some very interesting type of two-level system, which is vortices. Maybe you have heard that superconductors expel magnetic field. But that's only an idealization. So in reality, superconductors offer traps of magnetic field. And they trap it in form of some circulating currents, which last forever, which people call vortices. But these vortices, then they become a system on their own. They can actually give us dissipation and dephasing for our qubits. We can have just simply broken Cooper pairs by ionizing radiation, by high energy physics. We can have some molecules which are just sitting like water on top of the device. Or we can have all kinds of dangling bonds and dangling positional defects. So I see a lot of people in the room are, oh my God, what is this? Like, how do these things even work? It's true, it's amazing. It's amazing that on top of this complexity, we can still have quality factors of millions, and we can do gates with 3 and 4-9 fidelity. I find that amazing. But that doesn't mean this complexity does not exist. Right? I think maybe that's the main message that I want to convey. Things work quite well despite all of these things happening in the background. So now let's see what is an experiment that we can do to test this environment. Yes?
Two slides before, the publications were quite recent.
Yes.
Are all these effects known only since 2 years or a little bit over 2 years?
That's what we argued in the letter to the editor to publish our papers. So if these things would have been known already, the editor would have said, this is old physics. We're not gonna, it's not interesting. Right? So these things are new. People didn't really know about this. Of course, each of these publications has a very specific claim, right? So people knew about the fact that ionizing radiation can be a problem, but even that was not really well acknowledged in the community until a few years ago, right? But then here we showed a particularly striking effect I will discuss about, right? So this paper focuses on one effect of ionizing radiation on the qubits. There are similar papers with similar timing, 2022, 2021, from Google, from IBM, also discussing effects induced by ionizing radiation. Google has a paper which is called Catastrophic Errors in a Quantum Computer Due to Ionizing Radiation, something like that. Paraphrasing, it's not exactly the title, but the catastrophic errors is in the title. So yeah, this is new physics. Good. So how? Yes, please.
Sources. So obviously some of them were for sure in change T1 and T2 of your qubit. But are there, which sources are here significantly important in the sense that they form TLS with the same resonance frequencies of your substrate?
So what is significant or not doesn't necessarily come down to what is on resonance or not. Right? So actually, I will show an example where TLSs which are far off resonant give very clear and dominating effects. Right? So what is dominating is always a very important question to answer, and resonance is one of the most important ingredients, of course. But there are other ingredients, right? It depends also on how long-lived is your TLS. It depends on how strongly coupled it is. It might be on resonance, but if it's weakly coupled, we don't care about it. Right? It depends on how susceptible this TLS is, even if it's resonant, how susceptible it is to external factors. But it could be that you can easily tune it away with some electric field or with strain. These are experiments that the group of Alexei Ustinov is doing in Karlsruhe. So what exactly dominates your loss and your dephasing is usually a question that is very difficult to answer because you have multiple factors and you have multiple sources and they're all in the same time. So you can imagine that you're trying to navigate in this multi-dimensional space and you're trying to figure out which of these effects is the strongest in this multi-dimensional space, but they're all non-zero, right? So you have to navigate somehow and find which one takes you furthest away from where you want to be. And that's basically how we do our experiments. We try to imagine new ways of pushing the qubit in one direction or the other, which makes it more or less susceptible to one of these decoherence mechanisms, such that we can learn which one is more important and which one is not. So it really depends. To give you a concrete answer to your question, sometimes when positional defects are really on resonance with a qubit and they are strongly coupled, they will be dominant. They are relatively short-lived. So if they are on resonance and they split the line of the qubit, they will not only introduce dephasing, they will also introduce losses. But if they're not on resonance with the qubit, then these guys might be the dominant ones, or these ones might be the dominant ones. Okay, so let me give you an example of one experiment which will sound very familiar at the beginning, and then you'll see it gets a bit more complex, that we do to characterize our qubits. So the simple experiment that you could do a pi pulse. So just take the qubit from the ground state to the excited state, wait for a while, see how long it takes to decay. Right? So that's a T1 experiment. What we will do now is something a bit more sophisticated, is that before doing a pi pulse blindly, we will interrogate the qubit. We will ask, with this pulse, we're sending a readout, tone, and we're interrogating the qubit. We're asking the qubit, are you in the excited state already, or in the ground state? And if the qubit is already in the excited state, there's no need to apply a pi pulse, right? And then we just leave it in the excited state. And that actually gives us a higher fidelity for the excited state preparation. You see, we're not applying a blind pulse, we're applying an active feedback pulse. And we can, we can do that using these homemade parametric amplifiers, which we call DJs, dimer Josephson junction array amplifiers, which are also developed in our group, and which look very much like you would expect an amplifier to look like. It's some wire bonds on some strip line on a chip. And this is not the subject of this talk, but ask me if you want more details. What is in this strip line, it's also Josephson junctions. It's also some nonlinear medium which allows us to amplify. Now, the reason why you see here the profile of Leo Szilard is because what I have described here, this active feedback, where you apply a pi pulse if the qubit is in one state or not, this is the first step in a so-called Szilard engine, which is a kind of Maxwell demon. Right? If you think about it, the Maxwell demon was also this entity which had full access to the information of the system. And if a molecule was going from left to right, it was opening the gate. If not, it was keeping it closed. And in this way, it could push the system out of thermodynamic equilibrium. Okay. So this is what we're doing also here. We're looking at the state of the qubit, and but because it's quantum, then we call it a Szilard engine. And based on the information that we acquire, we can keep the qubit for a very long time in the excited state, just with active feedback. We can just keep asking, are you in the excited state? Yes, good. No, go there, right? And then keep repeating that. Okay. So that's what we do, and in practice, this is done with an FPGA board because everything has to happen much, much faster than the qubit T1, which is some, let's say, tens of microseconds up to hundreds of microseconds. So the feedback loop here, it's like a few hundred nanoseconds, right? And for that, you need fast electronics. and we are developing these electronics at KIT in an engineering group, but what you see here is a commercial quantum machines instrument, FPGA instrument. And this is the result of the measurement. So what we do is a reflection measurement. So and we get points in the quadrature. So what you see here is the different vectors. So all the vectors, all the reflection measurements in this area correspond to the qubit in the excited state, or all the reflections in this area correspond to the ground state. That's how we do a qubit measurement. It's just a amplitude and phase response of a microwave pulse. Does that sound reasonable to everyone? Yeah. And now, after the pi pulse, you see that we have changed that distribution quite a lot, and we can prove that we have placed the qubit with 96 or up to 98% fidelity in the excited state. Good. So now let's run this object for a variable number of Szilard engine cycles, right? So one cycle is one preparation, but you can run it more and more and more preparations. And after that, what we do is we just monitor. So we're just doing monitoring, where we simply ask the qubit in which state you are, and we don't apply a feedback anymore. We just record the state. And that's what it's called a quantum John trace. You can see it here. And you see that the qubit is in the excited state for a while, then it goes to the ground state, then it goes to the excited state, then to the ground state. And from these populations, we can get the effective temperature, which is about, in this case, 28 millikelvin. Not too far from the fridge temperature of 20 millikelvin. So, what I'm showing here is the simplest one round of the engine, which basically corresponds to a T1 measurement. So for anyone here who has worked with qubits, this is a T1 measurement. Okay. And you see that the qubit starts in the excited state, then it decays, and it's almost fully decayed, but not really, at 300 microseconds. And then we have to wait 10 milliseconds for the qubit to fully decay. So that's why we changed the axis here to log scale, so it can fit. Otherwise, the axis would go to some different room at the end of the building. Okay. So that's what I'm showing here. And now, with different colors, I will show you what happens when we run the engine. So before this waiting time, I run the engine several more times. For a textbook qubit, nothing should happen, because the qubit should have no memory. So the qubit doesn't care that it was in the excited state for 10 milliseconds before I start measuring. It only cares that now it's in the excited state, and now I start measuring, so it will start to decay with some T1. That's it. That's the only thing that it should care. It should only live in the present. Okay? So let's see what happens. Something happens if we apply 10 pulses. Something even more happens if we apply 100, 1,000, and even 10,000. Okay, so one interpretation, which was the interpretation of the MIT group when they first saw this with a more simple experiment, let's say, in 2016, the MIT group interpreted this, and justifiably interpreted this in a very optimistic note. Let's say they were saying, oh, T1 increased, right? I mean, what we see is a slowdown. This is a slowdown of the relaxation. I would have said the same thing, right? And that's actually exactly what I said when we measured this in our lab in around 2020, 2021. I was like, great. Well, I was already looking for beach houses, you know, like this looks nice. It's a very good qubit. You apply some pi pulses, and T1 increases by a factor of 10. Great. Okay. Okay, but now let's do a control experiment. If this is really T1, then we can do exactly the same preparation, but the last pulse, at the very end, instead of leaving the qubit in the excited state, the very last pulse, out of these 10,000, let's say, the very last pulse, we just decide to tell the qubit, go to the ground state, just for fun. We can do that. We can apply an additional pi pulse. Now, if this is T1, again, the qubit should have no memory. If this is T1, then the qubit should just like slowly relax to thermal equilibrium. That's the definition of T1, thermalization. Okay? So if this is indeed, so the interpretation until our paper, the interpretation for this curve was when you apply these pi pulses, you're moving away some TLSs or some quasi-particles. You're moving away some junk from around your qubit. You're giving it some kicks with your pulses such that your T1 increases. So it was a very optimistic view of the world. Okay? And if that's true, we should, when we start from 0, we should stay very close to 0 until we reach the end here. But that's what we measured. You see, we start from 0. Look at the dark curve. We start from 0. Quite spectacularly, we shoot up beyond 50-50. Think about that. Our qubit goes beyond 50-50, beyond infinite temperature, just under the influence of the environment. Right? So what happens, now we see a completely different story. Now we have a completely different understanding of what is happening. What we have done during the Szilard engine turns, what we have done is that we have kept the qubit in the excited state for a long time. The qubit imprinted that state in the environment, so basically it heated up the environment, so much so that the environment, even the environment is now in a population inversion state, and the environment is very long-lived. The environment takes 10 milliseconds to decay. And so this is even 50 milliseconds actually. So the environment takes a very long time to decay. So now when we put a qubit in the ground state, the qubit will immediately go to, to the temperature of the environment here, and then slowly together with the environment it will decay. And this will be a non-exponential decay, and we can model it and learn a lot from it. So I skipped the details of how we model this, but from this we can model that we have a ladder of TLSs, and these are not dielectric TLSs, by the way, right? So these dielectric TLSs would be short-lived, as I mentioned. They would never live for like tens of milliseconds. So these are probably spins with a very low coupling. So we never see anti-crossings. We never see split lines from these TLSs. But if these TLSs would not be there, our T1 would be basically 100 microseconds. And in this case, the T1 was something like 25 microseconds. So if I summarize what I've said, we have a bath, well, not a bath, but a collection. So these are some tens of TLSs, so not that many. We have some tens of TLSs which live forever. We model them as lossless. They have no loss, which live forever. And they constitute the main loss mechanism for our qubit. So a bunch of infinitely lived systems are the main loss mechanism for our qubit. So you can, this sounds not intuitive. Like the first time I said this out loud, I was like, something is wrong, right? Like if something is your dissipative environment, you would assume that it's a dissipative environment itself, but no. The dissipative environment for your qubit might be something that lives forever. And it's still the dissipative environment for your qubit. And it's actually bad. The fact that it lives forever, it's bad because it means that that energy comes back to the qubit. And it gives you some echoes in the quantum jumps, and it gives you correlations in time. Yeah?
Even with just one pi pulse, the qubit population is already 0.1% when you start in the ground state.
You mean
bottom left.
Here or
Yes. Yes.
No, this is, sorry, no, this 0.1% here, this just comes from temperature. This is just temperature. So the frequency of the qubit is not much higher than temperature. So in thermal equilibrium, you have 10% population. But this is the same for basically all superconducting qubits have some terminal excitation or some non-equilibrium excitation. You should never do a qubit initialization just by waiting. That's really not the way to do it. Because when you wait, the qubit doesn't go to 0, it goes to whatever equilibrium is. Or it might actually be out of equilibrium. So in a transmon, this is a few percent, that's true. In a fluxonium, because the frequency is lower, it's more like 10%, but it doesn't really matter. With the way you do quantum state preparation should always be with active feedback or with some active state preparation. Yep.
So you say it's a bug, yes, of course, if I want to operate on the qubit, but if it's idling in an algorithm, it can be a feature, right? So if you thought about like how to stabilize idling qubits in an algorithm with them?
In which sense this could be a feature? What do you mean?
Yeah, I mean, for them, like, even if they would decay or flip, I mean, it's not T1, but if the environment stables the not used qubit in the algorithm, it can be used as a kind of a mitigation technique.
I doubt it, and I don't really know how you would do that, but I'm happy to hear ideas. Because what what happens is that you have a constant back and forth between the qubit and this environment. So whatever goes to the environment, it cannot die, which is actually what we would want. We would want whatever goes to the environment to never come back. It comes back to the qubit, and then because these TLSs are the main loss mechanism for the qubit, then the qubit again decays there. So there's this constant ping pong between the qubit and the environment, which happens behind the curtain. We don't see it, right? And the fact that we don't see it, it's another way of saying that it's completely incoherent from our point of view. That's the quantum mechanically, that means we lost track of the phase, and we don't know what's happening, and that's just bad. So that's game over, basically, for quantum information processing. If you're trying to build a battery, so if you're trying to just store energy incoherently, then that's fine, that's good.
What I'm talking about is if you have a qubit in the one state,
Yep.
and it should last in the one state for a long time
Yes.
because you're not using
Yes?
it, can I not use like
No.
this mechanism?
It's an illusion. This is an illusion. So the fact that this that's basically how people got tricked. So the fact that this curve decays very slowly, that doesn't mean that the qubit stays in the excited state for 50 milliseconds. Not at all. It just means that the population of the ensemble is hot. But you see, if there's no board here, but you can have for the same population, right, which is, let's say, a population very close to 1, so very close to this value, it can be like 1 basically constantly all the time, and then 0, which is what you would want, long T1, or it can be 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. But on average, the 1 is the dominant, right? And this constant jumping, that's game over. And that's what's happening. There is a constant jumping here with T1, which is very short compared to these time scales. So, right, when I told you in my introduction that we think we understand quantum mechanics, but we have a poor intuition of it, that's exactly what I was talking about. Like, we do these measurements, we see them and we're like, how can this be? And then if we think really hard about it, then we understand what's happening. But our first instinct is often wrong, actually, in these experiments. All right, so I'm looking at the time. Okay, so the second and third parts are much faster, but let's see, we don't have to go through all of it. Is there a cutoff? I mean, I could also just stop here. Yeah, oh, okay. So now let's talk about something else. So when we look at a qubit, we like to look at quantum jumps because we like to look at traces like that because they give us a lot of information about the time dynamics, what is happening to the qubit population at every moment. And if we just look at how these jumps behave in time, we see that we have some what we call quiet times, where from the quantum jumps, we get a nice Poisson statistics. And then all of a sudden, the next hour, it's noisy. Sometimes it jumps a lot, then it gets quiet, then it jumps a lot, then it's quiet. And then it gets quiet again, and we don't know why. So this can also be seen in the statistics. So if you just look at the statistics of quantum jumps, what you should see here is exponential decays, which should look constant, but they're obviously not, right? So obviously, if I do the statistics of quantum jumps, it changes drastically from 1 second to the next second. Okay, you see, it's jumping all the time. And if I do exactly the same experiment, just 1 hour or 2 hours later, this is what I see. Way more quiet. It's still not perfectly, each measurement is not perfectly identical with the next one, but it's much, much more stable and more quiet. And we have changed nothing in the setup. Everything is the same. So clearly there is something that we've hidden under the rug, which is now trying to get out and spoil our measurements. So fun fact, we would expect these decays to be perfectly exponential, and they're not, because you see in this log scale, they're bending in the quiet times, but that we can explain. So with the model that I told you before, with this model of environment having a memory, we can actually calculate and we can predict the shape of these distributions and we can understand it. So that's fine. So that's not a mystery. Why it's not exponential, it's not really a mystery. The mystery is why it's changing all the time, right? And then why it stops from time to time. So why? Yeah. And for that, we decided to go one step lower in complexity and not look at quantum jumps. We just decided to look at currents in our devices. So we can build a qubit which has only one loop. That's what I've shown you before. Or we can build a qubit that is called a gradiometric, where the junction is in the middle, and everything else around here is a superconductor. And if we cool this object in field, we can trap some flux in this big loop. And by trapping some flux in that loop, we're biasing the qubit to the working point. You don't have to understand the details. There's a bit of funky superconductivity involved in this initialization. All you need to know is that if we cool down in field, we trap some flux in this superconducting loop, and that flux should live there forever. It should be a so-called persistent current, which is not allowed to get out because if for magnetic flux to get out, it will have to interrupt this superconducting line. It will have to break superconductivity, which costs a lot in order to get out. So that's what we do. And the way we show it is by basically looking at these patterns. So we have some flux dependence of our readout resonator, which looks like this when the qubit is biased without a flux trap. And then when we add a flux trap, it's basically inverted. You see the flat part is here, it's like below, and the flat part here, it's above. That's all I want to show. So this is the proof that we have trapped a fluxon, and we have trapped the flux, and it lasts for about an hour and a half, and then it escapes. So this measurement was done in the lab in Karlsruhe. So what we learned from this is that a current, a superconducting current, which should last forever, really forever, it only lasts for 2 hours, and then it escapes. And that's weird. It should not happen. If you do the calculation, this energy scale should be completely irrelevant. So maybe we didn't do enough shielding. So then we added, this is the kind of shielding. This gives me the opportunity to show you how our setup looks like. So we put our samples in copper boxes, which go inside a superconducting shield, which is the aluminum on the outside. On the inside, it's copper. And then everything goes into a mu metal shield. This is just a high permittivity alloy, very soft magnetic alloy. And then maybe that's not enough. So maybe we need a better shield. And the ultimate shield, when it comes to muons, it's a mountain. It's the Gran Sasso mountain in Italy, which is actually easily accessible. There's a lab right in the middle, below 1.6 kilometers of rock, so below a lot of rock, old granite. There is a lab, and this lab is connected to the main tunnel through the main highway under the mountain. So the access is very easy. It's just an exit off the highway. Right? So that's very nice. So we can go underground, do the same experiment, and now you see it lasts forever. So this is 62 hours. That's several days of measurements underground, no problem. Okay. So after that, the people who are running this underground lab, they were like, oh, that's very exciting, but maybe we should do something else than just waiting. So then we added some very weak ionizing radiation source, which is not even a source. It was just a drill bit from Bauhaus, right, which has some tungsten in it, and it has some isotopes. And you just bring that close to your fridge, and then bam, you see that it starts to jump. So you start to pull current out of the qubit and push current into the qubit. So that's the proof that what is happening is that ionizing radiation is breaking our persistent currents. And we will see that also. Of course, if we see it in the biasing, in the current bias, we will also see it in the quantum jumps of our experiments. Okay, so the last thing that I wanted to talk about in the last 5 minutes, this is the third part, is the fact that the cosine phi current phase relation of our junctions is probably, I mean, in most cases, it's probably not cosine phi. So the spectrum that you calculate with just cosine phi, it's not accurate. That's the thing. So this is only true if this barrier, it's in some sense an approximation, if this barrier is consists of many channels with very low transparency. But if you have some inhomogeneity, you have some transparent channels, those will give you some additional terms to the cosine. So the intuition is the following. So ideally, when you deposit these aluminum electrodes, you would like them to be like the salt flat plains in the US, for instance, in Death Valley, where, as far as you can see, it's just completely a completely flat surface. They use this surface actually to do car races and to break world records for speed on land, and that's what you would like to have. But in reality, it's maybe more like the Red Rock Canyon, where you have all these boulders and there's a lot of inhomogeneity. So when you oxidize this, you will have some defects and some inhomogeneous oxidation, much more than you would expect if you had a really flat electrode. So that's maybe the mesoscopic intuition. And if you have that, this relation, you would expect that this relation will fail at some point. So how do we test it? Well, the way we test it is that we simply take some qubits and we measure the spectrum. We measure the transition 01, 02, 03, 04, and so on and so forth, and we compare it to the calculation. So this is not a complicated formula. It's a very easy formula. So we can calculate exactly the spectrum of the qubit, and we can plot measurements versus spectrum, and that's what you see here. So the y-axis is the deviation between what we measure on our qubits and what we expect, or what we fit. The first 2 points will always fit because we have two fit parameters. We have the inductor and the capacitor, right? So because we have two fit parameters, we can always fit the first 2 points. But then the other points should line up because there are only two objects here. There's a capacitor and an inductor here. But they don't. Okay? So you could say, okay, fine, this is just one sample measured at KT. So we measured a bunch of other samples. They change. Okay? They also don't fit. Then we talked to people from colleagues from University of Cologne, from École Normale Supérieure in Paris. They measure the spectrum on up to the 6th transition, and they also see these deviations. And these deviations are big, by the way, right? I mean, these are 50 megahertz. You can easily see 50 megahertz. And then we're like, okay, there are all these IBM processors. Let's ask some people from IBM for a collaboration. So the people in IBM Yorktown Heights were very positive and very willing to collaborate. And we had an intern who was our liaison to IBM, and they did these measurements on their qubits on the processor named Hanoi. And this is what you see. So you also see a lot of deviations. It's a bit interesting that their deviations are sometimes in the same direction that we see them, but often actually in the opposite direction. So that points to some interesting difference between their junctions and our academic junctions. We asked them, of course, about it, but they are not allowed to show us their junctions, so we never saw their junctions, how they look like. So we can only speculate about why, but clearly it also doesn't fit to the standard model in these qubits either. Yep.
It looks like the 0 to 1 transition is always very good with both model and the experiment.
So 0, 1 and 0, 2, by default, they will always fit.
Yeah.
Because we have a 2 fit parameter, and 0, 1 and 0, 2 are the 2 points that we use for the fit.
But then why do I need to bother about the 0 to 4, 3, 5? Because they are not in my computational subspace.
Yes. So what the reason why you need to bother is because if you have these two, the fact that you can get a perfect fit with two fit parameters for two measurement points, this is not something that you should feel comfortable with. Right? Whenever you have a physical model where you have two parameter fits and you test it with 2 points, you should not feel comfortable about that, because it will always work, right? So I could put here whatever other model. I could put here whatever model you want, almost, and it will still fit, because it's two parameters and 2 points. Right? So that's why you care about it, because what that tells you, the fact that the higher points don't line up, what that tells you is that your Hamiltonian is wrong. And that tells you that your EJ and your EC that you're fitting will also be wrong. So the direct consequence for your computational space is that your computational space, your 0, 1 and 0, 2, 0, 1 transition, is not what you think. You know, that what gives that transition, the EJ and EC corresponding to that transition, is not what you think. So the charge dispersion will not be what you think. The noise will not be what you think. So that's, in a way, the most naive consequence. But as soon as you go into details, you realize that none of these objects are qubits. They're all multi-levels. So even if, let's say, from a computational point of view, you only care about 0, 1, the dynamics of 0, 1 will never be disentangled completely from the dynamics of all the other levels. You will always see leakage to the higher states. So for instance, in the latest paper from Google, the only way in which they could make error correction work in their new setup, like the first step towards error correction work, is because they handled the leakage to the higher states. So the higher states are really important to know. Okay? So now let's add more parameters to the model. So we
concerning the color code, like
sorry, yes.
Also on your side and on IBM side, is it the same chip measured at 3
yes.
different times?
Yes.
Like,
so in our case, it's actually the same qubit, which while it ages, it changes parameters. So you could say it's a different qubit because the EJ changed, because it aged. And we also thermally treated it once to shift it even more. So it's 3 different qubits, but it's the same electrode. It's the same metal in some sense. For IBM Hanoi, it's 20 different qubits. They just have 20 qubits on the chip, and we measured all of them.
Yeah, asking because you want to check like the Hamiltonian. So, do you have an indication of time dependence in this Hamiltonian?
So yes, from our qubit, which was the same object measured 3 different times, you can see changes from cooldown to cooldown. Yeah. So how can we solve this? Well, we add more fit parameters. Okay. So we add what we would expect to have, which is some kind of higher components, higher harmonics. So it's not just cosine phi, it's cosine 2 phi, cosine 3 phi, which correspond to tunneling of not one Cooper pair, but pair of Cooper pairs, triplets of Cooper pairs, quadruplets of Cooper pairs. That's what these harmonics, physically, that's what they correspond to. And if we have this model, everything can fit. Right? Which is maybe not that surprising if right now we have 4 fit parameters, 4 points. So maybe that's not that impressive. And that's my point. My point is not to say that we can fit this. Actually, my point is to say that with only 2 parameters we cannot fit it. That's the point. So there is more complexity hidden from these harmonics. So I'm not claiming that we have fitted these harmonics. So these EJs would be some percent level. What I'm claiming is that you should be aware that they are non-zero. Yep.
I mean, the ENS values show that. I mean, the model works better because you can predict like the 0, 5 and 0, 6 transition better from the first 4. So
true.
This is somewhat
that is true. That is true, yes.
What happens if you use other transitions than just the first 4 transitions? Like, for example, 1, 0, 1, 2, and 1, 5, and 1, 6.
No, those are determined. So those are determined actually. So the spectrum. So these transitions determine entirely the spectrum. because the 1 to 4 will be just determined by these differences. Right, so whether I look at 0 to 1 and 0 to 4, or whether I look at 0 to 1 and 1 to 4, the difference will be predetermined by, it's just two numbers, which just have to add up. So nothing will change.
That's clear. So you use, for fitting the parameters, you use 0, 1, 0, 2, 0, 3, and 0, 4.
Yeah.
Probably. Why not using 0, 1, 0, 2, and 0, 5, and 0, 6?
Ah, if we skip one of them. I see. We have not done that. The reason is that the lower, one technical reason is that the lower the transition is, the more accurate it is and the easier it is for us to measure it. So we're always pushing to add one more transition. We have to push the technology. And that's what, for instance, that's what the internet IBM has done. They really had to work a little bit on their electronics, which is custom designed to work in the computational space, right? It's not designed to work to measure the fourth level. And they had to do a bit more effort to actually provide spectroscopy for the fourth level. So it's always more work to go higher. And at some point, the potential ends, right? So typically you have square root of EJ over EC levels in the well. So if your EJ over EC is 25, then you have 5 levels. Above that, you're really in the continuum, and you're very sensitive to charge offsets. And even before that, when you go to higher levels, you are sensitive to the charge offsets. So I think this was my last slide. So the conclusion here is that I'm not trying to convince you that you can fit the harmonics. What I'm claiming is that they exist, and they change the spectrum, so you should be aware of it, and they have real-life consequences. So since then, what we have done is that we have measured we have measured the charge dispersion of these levels. So for the experts in the room, these levels are not unique. They depend also on the charge offset, so a voltage gate, if you want. And you have 2 levels depending on the parity. So if you add that information to the fit, then you can be much more accurate with the harmonics fit. And you can actually get the harmonics. And in a follow-up work, which will be on archive in a few weeks, we will show that fitting these harmonics is essential if you want to understand the readout of your qubit. So if you want to understand the demolition effects and to avoid them when you read out the qubit, you need to know about the harmonics. You need to know about the higher spectrum. So with this, I'm done. So I have shown you that a Szilard engine can uncover hidden environments, which if you just do a T1, you might miss. There are, if you know what to look for, there are signs even in the T1. You can see it's non-exponential, and the last decay is very slow and polynomial. But with a Szilard engine, it's in your face in some sense. It's very obvious. Remember that phonon shock waves above ground are always happening in your device. So you have to radiation harden your device if you want to cope with these phonon shock waves from ionizing radiation. And last but not least, if you want to have a complete understanding of your Hamiltonian, remember that your cosine phi Josephson effect is not complete. Depending on the mesoscopic reality of your junction, you might have higher harmonics in the Hamiltonian. And this is a recent photo of the group. And with this, I would like to thank you for your attention.
Thank you very much, Professor Pop, for your talk. We're already a bit over time, but we can maybe make time for 1 or 2 more questions. Are there any questions right now? Yes, please.
So you've shown that there are many problems in building a single qubit superconducting. So I wonder, will we ever see superconducting quantum computers that lived in this era?
You're asking me to predict the future. So I don't know.
But do you have a feeling?
I can tell you what I feel every day. I feel excitement, and I feel intellectual stimulation from measuring and understanding and modeling these devices. And what I can also feel is that there is a huge progress from year to year, from decade to decade. If I look at the experiments that I was doing 10 years ago, the level of complexity and the level of understanding that we had 10 years ago is not comparable to what we have now. Right now, the progress has been huge. And if I look 20 years ago, we're not even talking about the same experimental techniques anymore. Right? Now everything is RF. 20 years ago, all the qubits were measured in these quasi-DC measurements. So given this very steep progression curve, I'm optimistic. And if you ask the qubits, the students in our labs, they seem to be happy and optimistic and intellectually stimulated by the physics that they're doing every day. And I think that's all I can say about the future. I'm convinced that this will continue in the future. I can see beautiful physics and I can see big breakthroughs in the future. Whether these breakthroughs will lead to a fully fledged error-corrected, fault-tolerant quantum computer that runs Shor's algorithm in the next 10 years or in the next 20 years, I don't know. I don't think it's impossible. I don't think it's impossible that in 20 years we have a fully fledged quantum computer that actually runs Shor's algorithm and breaks encryption and allows spy agencies to look at the encrypted data from 20 years ago, or like from now. I don't think that's impossible. I think there is a distinct chance that that will happen, but it will not be easy.
Yeah. Yes, one last question.
So, from our understanding, most of the talk was on single qubits. Do you know how to scale to a system with more qubits, or do you plan experiments to understand this type of problem?
Yes, of course. So that's what I was alluding a bit in the introduction. It is important, and I really appreciate the fact that there is an effort in academia, but also in industry, to scale these devices to a handful of qubits, to some tens of qubits, because there are some phenomena which emerge at scale. So I don't think we are ready, and I don't think we should rush necessarily to get to 100 or like hundreds or thousands of qubits right now, because the complexity will just be overwhelming. Right? But if we go to 5 qubits or 10 qubits, there are very interesting phenomena that we can see them, which we will not see on 1 qubit. A very simple example is correlations. Right? So if you have errors, this is what the Google group has shown, and also the IBM group. If you look at 10 or 20 qubits on a chip, when you have a muon going through the chip, you can actually see that there's a phonon wave which activates errors as it propagates. You can see in time how errors are activated across the qubits on the chip. And this will be correlated. So for that, of course, you need multi-qubit devices. And this is just a very simple example, but there are more interesting examples which involve entangling 5, 10 qubits, and then looking at how the environment acts on this highly entangled state. And I'm really looking forward to doing these experiments in the next, let's say, decade or so.
Okay, then thank you again very much, Professor Pop, for your talk.
Thank you. This was very fun. Thank you for all the questions. Yeah.
In our next colloquium on the 5th of December, we will have Professor Barbara Kraus from TUM here, and she will be talking about how you can validate the correct functioning of quantum devices. Okay, thanks for your attention and have a nice afternoon.